Hello everyone, today we'll be going over 2D projectile motion. First of all, we'll cover basic knowledge that you need to know before you tackle 2D projectile motion problems. Then we'll be going over what 2D projectile motion exactly is and the assumptions underlying it. And then we'll go over steps to solve 2D projectile motion, and I'll walk you through some examples. Alright, first let's go over the basic knowledge you need to know before you tackle 2D projectile motions. First of all, you need to understand the kinematics equations, which is what I've written down below. You need to understand what all these symbols mean, and you need to understand the fact that because these are vectors, we need to allocate them positive and negative directions. Additionally, you need to understand some basic knowledge of vertical motion. When we have an object that's on Earth, the acceleration is always the acceleration of gravity, which is g equals 9.81 meters per second squared, always directed downwards, of course. Here I've drawn a diagram to show you how this downward acceleration affects its vertical velocity. So here we have this ball that's being thrown upwards. It initially has a really high vertical velocity, and as it keeps going upwards, you can see that its upward vertical velocity decreases because acceleration is going downwards, which goes against its upward motion. When it reaches its maximum height, you can see it has a vertical velocity of 0, and then because the downward acceleration has really just stopped its upward motion and it's reached its maximum point that it can go upwards, and then it begins falling downwards. Going downwards, you can see its downward vertical velocity increases over time because of the downward acceleration. I talk about this more in my video of kinematics basics, so if you want a more detailed overview of all this information, please go to the video. I'll link it in the description. Alright, so now let's go over what exactly is 2D projectile motion, because we can't exactly solve questions on 2D projectile motion without actually understanding what it is. 2D projectile motion is, as it says, it's motion in 2D. No longer do we have to think about balls that are thrown only vertically or cars that are only going horizontally. We have to look at both horizontal and vertical motion. So this is more realistic in terms of projectile motion, because oftentimes when we're throwing something, we don't just throw it vertically or just throw it horizontally. It's going both vertically and horizontally. So that is what 2D projectile motion is all about. Alright, now let's go over some underlying assumptions in 2D projectile motion. These assumptions are actually closely related, as you will see later on. The first assumption is that no air resistance or friction acts on the projectile. Only gravity acts on the projectile. The second one is that horizontal velocity does not change throughout the projectile's trajectory. So this first one actually directly causes this one. And how can this be? If you think about it, let's say you have a ball and it's going both horizontally and vertically. Gravity, as we know, acts downwards, but it doesn't act horizontally in any way. Gravity does not go to the right or to the left. It does none of that. So it only affects the vertical component of the object's velocity. And per Newton's laws, we know that if no force acts upon an object's motion, then it must move at constant velocity or be at rest. And since it was moving at constant velocity, therefore the horizontal velocity does not change throughout because no force is acting upon it when we assume that no air resistance or other drag force acts upon the projectile. Now this has a few consequences when we're doing calculations, because when we do calculations, we use our kinematics formulas. We use formulas like V equals U plus AT, or this one right here, just all the kinematics equations that we're very familiar with. Well, this no longer applies for the horizontal motion because there's no acceleration. Horizontal velocity is constant, so A for horizontal equals 0. And this actually makes the horizontal calculations very simple, because then we can just move on to the simplified version of velocity, which is just the rate of change of displacement, which is S over T. So really, when we're doing horizontal calculations, we only need to know this formula, and we can just manipulate it to find the horizontal displacement or the time. Whereas for vertical, because there's an acceleration, we have to use this. We have to use our conventional kinematics equations. And we just sort of have to manipulate these to get what we want. Really important thing to note about this is that horizontal and vertical are completely independent. And this is just to say that its horizontal velocity does not impact its vertical velocity. They're completely independent of each other. The only variables they would share in calculations would be time, because you could be calculating for its horizontal velocity at a certain time and its vertical displacement at that same time. So that's the only variable they could share, but otherwise they're completely independent from one another. All right, now we'll be going over the steps in solving 2D projectile motion. If you looked at my kinematics basics video, you'll see that these are very similar steps. There's only a few little tweaks in there. So the first step is choose a positive and negative direction for both vertical and horizontal directions. So up, down, left, right. Then you'll split your kinematics values to vertical y values and horizontal x values. You'll write down the vertical and horizontal values that was given and your unknown. And then referring to the horizontal and vertical kinematics equations, use the equation that best fits your known value and unknown. Just like basic kinematic questions, you're going to have to use some trial and error to get what you want. But again, as I mentioned the assumptions, remember horizontal, you just use the basic V equals S over T, and then for vertical, you use your basic kinematics equations. All right, now let's do some example questions just to give you an idea on how these steps work. So, an object is fired horizontally at a speed of 300 meters per second from the top of a building. The object lands 900 meters from the base of the building. What is the height of the building? So I'm just gonna draw a diagram just so we can visualize it. So we have an object and it's fired horizontally at 300 meters per second, and it keeps falling, and then it lands 900 meters from the base. And we want to know the height of the building, which I'll go SY. So let's first identify the positive and negative direction. I'm going to say that down is negative and up is positive. And even though there's not explicitly any right or left, the other problem we'll be looking for does have left or right. So I'll just say right here, I'll make left negative and right positive. All right, now that we have put our positive and negative directions, we need to write our values that we know and our unknowns. So let's put our X and our Y. So we know that its horizontal velocity was 300 meters per second, and we know that it landed 900 meters from the base of the building. Pretty good for the horizontal component. Now for the vertical component, what would be its initial vertical velocity? Well, because the object was fired horizontally, its initial vertical velocity would be 0 because it had no vertical velocity to begin with, it only had horizontal velocity. As for acceleration, we know that its acceleration would be the acceleration of the planet that is on, and well, we're going to assume this is Earth, so this would be 9.81 meters per second. Note that I put a negative here because acceleration is moving downwards. All right, so we want to know the height of the building, so this would be SY. However, we might realize there's a problem already. We only have 3 units here, and we need 4 units, 3 knowns and 1 unknown to use any of the kinematics equations at our disposal. So how are we going to fill in that 3rd known unit? Well, this is when the horizontal component of calculations comes into play. As you can see, we have our horizontal velocity and horizontal displacement here, and we can actually use that to calculate a value that they both share, both the horizontal and vertical component, which is time. This is something they will both share. This is the only value they both do share. And using that, we can find our 3rd known value to find our unknown vertical value. So let's try that. So we know that Vx equals Sx over t. So then t is just Sx over Vx. So therefore, t is just 900 divided by 300, which gives us t equals 3 seconds. So then this is no longer unknown. We can say that this is 3 seconds. All right, so now we can go look at our vertical component here, and we can look at our kinematics equations that we can use to solve for the displacement. So I'm going to assume that S equals ut plus 1/2 at squared works the best here because it has all my values. So Sy, because we multiply by 0, this is just 0. And this gives us negative 44 meters. And you might be confused why this is negative. Well, it's negative because I stated that downwards is the negative direction. So this is stating that the object moved 44 meters downwards. But because we're looking at the height of the building, we'd have to make this positive. So we say, therefore, height of building is 44 meters. All right, now let's look at our second example, which is slightly more complicated. A stone is thrown upwards into the air with an initial velocity of 45 meters at 20 degrees above the horizontal. What was the total time the stone was airborne, and what is its maximum height? Okay, this one is slightly more trickier, but let's draw it down to give an idea. So we have a stone. It's thrown at 45 meters per second at 20 degrees above the horizontal. Now here is where you have to pay attention to the horizontal and vertical components. We can't say that 45 meters per second is our horizontal velocity or a vertical velocity. We have to actually use the angle here because we have both a vertical and a horizontal component here. We have an initial vertical component, which is this, and we also have a horizontal velocity, which is right here, and we have to take that into account. So here we can sort of just use basic trigonometry to get this. So we can just use basic SOHCAHTOA to get an idea of your initial horizontal and vertical, not displacement, initial velocities. So once again, I'm going to split this into x and y. So for our horizontal velocity, we're going to look at only this component. And using trigonometry, we know that cosine would give us this component. So this would be 45 multiplied by cosine 20 degrees because, well, SOHCAHTOA, we know that this is adjacent over hypotenuse. So cosine 20 degrees would really be Vx divided by 45, and move it over, Vx would just be 45 multiplied by cos 20 degrees. And we're just going to put this in our calculator to give an actual value, which is around 42.286 meters per second. Same thing we're going to do for our vertical component. So again, using our basic trigonometry, we know that if we had sine 20 degrees, this would be our vertical component here. So that would be u divided by the hypotenuse, which is 45. So u is 45 sine 20 degrees. Putting this in our calculator, we get 15.391 meters per second. All right, so now we're going to fill in what we have left. So we know acceleration would be 9.81 meters per second. Again, remember the negative. Well, now that we've written sort of what the question's already given us, now we have to sort of use some of our basic knowledge to get the rest of the values we need to calculate. So we know that from our overview of basic knowledge, when we have the maximum height, its vertical velocity is 0. And with this, we can now find its maximum height, sy. So actually in this case, we really didn't need to manipulate the horizontal component of the question because it doesn't really help us as much. However, I still recommend you put in your horizontal and vertical components because you never know if it'll come to use or not. So you may as well just write everything and sort of figure it out later on. All right, so now that we have all our values here, we can use our kinematics equations. So looking at our kinematics equations, I think this equation works the best. And now we can solve. So this would be 0. Which gives us around 12 meters. So this is its maximum height. All right, but how are we going to find the total time the object was airborne? Now, there's actually 2 ways to go about this, and I'm going to show you both ways just so you have an extra tool in your toolbox and you don't have to rely on only one way. So one way to think about it is, oh, I accidentally erased that too. All right, so here we have the trajectory of the stone. It starts here and it has an initial vertical velocity of u, and then it goes back to where it started at the end of its trajectory. Actually, its final vertical velocity in this case is negative u. Because acceleration is constant throughout, when it returns to the exact same spot to where it started, which is essentially the end of its trajectory, it has a final vertical velocity of the same magnitude of its initial vertical velocity, but just negative because, well, it's the opposite direction. So with that in mind, if we were going to find the total time, we would say that v equals negative 15.391. And this is just something that will always occur when it returns the exact same spot through which it was thrown. So with that, we can actually find the total time in between this, which was the total time it was airborne. So now that we have all our values, we can calculate. So let's use our kinematics equation again. This time we're going to use a different one because we have different values. This gives you around 3.1 seconds. Alright, that's one way to go about this, but as I said earlier, there are two ways to go about the same question. So another way to think about it is when an object reaches its maximum height, it's actually half of the time of its entire trajectory. So actually I shouldn't have erased that drawing, whoops. So we have its maximum height here. Now this is the total time of its trajectory, but when it reaches its maximum height at this point, this is actually half the time of its total trajectory. So if we found the time when it reaches its maximum point and double it, this would be the total time that the stone was airborne. So let's now try it this way. So now we're going to move v back to 0. Let's just separate this. Do the calculations again, but differently. This gives us 1.569 seconds, but because this is only half the time, total time would be double this, which gives us, once again, 3.1 seconds. So as you can see, there are multiple ways to go about this question. So always just kind of experiment and familiarize with different ways you can go about this, because physics, there's always a solution and there's multiple ways to go about it. So just kind of figure out what's most comfortable to you and really just get some tools in your toolbox, because it'll really help you with more complicated questions. That's basically all I wanted to talk about for 2D projectile motion. If you have any questions, please let me know and I'll try my best to answer them. Good luck.